So since the number of the rational points and the structure of the Riemann space we consider will be important in the structure of the algebraic geometric codes, I want to present one more family of the function fields that we know that we are able to compute their genus, and they have the maximum number of the rational places, and they have nice structure for the Riemann spaces we consider in their structure. So for this purpose, finally, I want to talk about a bit Hermitian function fields. So indeed, they will be a special case of what is called tame cyclic extension, but for the moment, we can consider them as spatial type of function fields, which are given the transcendental x and y, and that satisfies this equality. So here, PIs denotes the pairwise distinct irreducible monic polynomials. And A is an Algebraic constant. And indeed, these monic polynomials can have integer powers. And in general, for the simplicity, for this type of function fields, the characteristic of the constant field is supposed to be relatively prime of n, which shows the power of y, and each I is supposed to be relatively prime n again. And indeed, such extensions are also degree n extensions. And one of the special case of this type of extensions, indeed, for instance, if you recall the definition of the elliptic and hyperelliptic function fields, indeed, we have, in some sense, the spatial case of this type of extensions. So this carefree condition, for instance, in some sense, will correspond to this the condition on ni's being relatively prime. And similarly for hyperelliptic function fields, if you consider the equation y is equal to f of x. Here, f of x is a polynomial of degree 2g plus 1 or 2g 2 plus 2. They can be also give this type of spatial case of this type of extensions or the algebraic function fields. But for the coding theory point of view, there's another spatial case of this expansion, but this is not going to be so clear, which is given in lemma 6.4.4 from Stettenot. They are called, first they are defined over the constant field fq square. Here fq denotes a finite field. They are defined, this x and y have algebraic relation as y to the q plus 1. So here q denotes the cardinality of the finite field fq minus 1 minus x to the q plus 1. But if you see the literature of algebraic geometric codes which are derived from this type of extensions, This is not so that clear in general, but they are defined as algebraic function fields if q square of x and y satisfies the equal to y to the q plus 1 and x to the q plus 1. And okay, they are defined in terms of this equation, but moreover, we have also no additional properties for this type of algebraic function fields. For instance, their genus is determined by the multiplication of q and q minus 1 over 2. And the number of the rational places is q plus 1. And indeed, we can also describe these rational places in terms of a place at infinity. So the common pole of x and y. And for each alpha from the constant field, for each constant alpha, indeed there exist exactly q elements in fq square such that it satisfies this equality. And here, let me also note that this expression indeed can be also written as the trace of the finite field fq square over fq of beta. And indeed, all such pairs, so I mean, if you consider the all rational places like the defined by the alpha and beta, for all such pairs, alpha and beta, indeed, there exists unique place in this function field, in this Hermitian function field, such that when we evaluate them at function x, we get the x coordinate. And when we evaluate them at function y, we get the y coordinate. So that means, thanks to this structure, indeed we know the number of the rational places, and moreover we know that their structures, how we can describe them. And moreover, we also know that what happens when we evaluate the functions x and y at these places. And indeed, the number also tells us they attains the upper bound of the Husserl bound. So they are maximal in this sense. So this is advantageous because if you consider the Hermitian function field, and we know that the number of the rational places gives us information about the length of the algebraic geometric code, this structure gives us the maximal length, I mean, as large as possible, as long as possible. And moreover, if you consider the spatial divisor G, which will be important in the domain of the evaluation map, which is in the form of R times O. By the way, this O, or we can also show it Q infinity or O infinity. This is a place at infinity. This is RO or R Q infinity. They denote the same thing. In this case, we can also give the form of the basis of the Riemann space of L of G when G is of the form of RO, or particularly if it is degree R. So for each R, indeed, x to the I times y to the j, here is non-negative integer, and j is between 0 and q minus 1, and I times q plus q times q plus 1 is bounded above R. And these functions forms the basis of the Riemann space of R of O, or with the different notation R of Q infinity. And we denote our algebraic geometric code which will be defined by the divisors D. Here D denotes the sum of all rational places different from Q infinity or O. So that means they are going to be elements in FQ square that satisfies the equality that also defines the Hermitian function field. And here Q infinity denotes the common pole of X and Y. So the first, and for in general in the literature, this is denoted by CR and is called the Hermitian code. So first, let me give some remarks. We can do it by using our fundamental notions. We can easily observe that if R is less than or equal to S, then the Hermitian code, which is defined by RQ infinity or RO, is a subspace of the Hermitian code, which is defined by the divisor SO. And for some, if you consider some trivial cases, for instance, is if the degree of the divisor G is negative, we know that it gives us the trivial space. So that means there is no function to evaluate, and our Hermitian code will be trivial space. And if we suppose R is bigger than equal to, it's strictly bigger than Q cube plus Q square minus Q minus 2, indeed, this is equal to Q cube plus 2G minus 2. Here the G denotes the genus, which we define which we showed, which we supposed indeed as Q times Q minus 1/2. And by theorem 2.2.2, we know that the dimension of CR is going to be indeed the dimension of G minus the dimension of G minus D. And here, if we apply Riemann's theorem, indeed we can see that the dimension of CR is going to be Q cube, and indeed this is going to be length of our algebraic geometric code, because we consider it as evaluations at the Q cube plus rational places. So this shows us indeed, in this case, if CR is strictly bigger than Q cube plus Q square minus Q minus 2, then CR is nothing but n-dimensional vector space over FQ square. So if you want to get interesting parameters, so if you don't want to get trivial cases for a linear code, the interesting cases for R lies between 0 and Q cube plus Q square minus Q minus 2.